Alright, hello everyone. Today we're talking about symmetry. Okay, our objectives will be to identify line and rotational symmetries in two-dimensional figures, and then identify plane and axis symmetries in three-dimensional figures. So we'll be looking at, again, 2D figures and 3D figures, and the different types of symmetry we can have in those figures. Okay. So symmetry, that should be a familiar word. If you guys think back to Algebra 1 and think about graphing a parabola, guys. A parabola, that's the graph of a quadratic function, okay? Looks something like a U, could be upside down, doesn't matter. But I know when I teach graphing parabolas, I always teach the first thing you want to do is find this axis of symmetry. The algebra behind it is just, again, the points, it saves you a little bit of work because points, they map across there. It's symmetric. It's the center of the parabola. Points reflect across it, okay? So this symmetry is what we're talking about when we talk about line symmetry, okay? A point on one side of that line of symmetry, again, that axis of symmetry or that line of symmetry is going to be the perpendicular bisector of it. So it's kind of like a reflection in a sense, but in a single figure. Okay. So that's just kind of a tie into some things you've already learned about symmetry. All right. So taking a look here at our first key concept. So symmetry maps a figure onto itself. Okay. A figure in the plane has line symmetry or reflection symmetry if the figure can be mapped onto itself by a reflection in a line called line of symmetry, or axis of symmetry is what we call it for parabolas. So guys, here this figure they've got drawn, this kind of chevron type figure, as you can see clearly across that dashed line they've plotted. Okay, that line of reflection, if you will, or line of symmetry, it's the perpendicular bisector of points. They map onto each other, and this is going to be true for any point on this figure. That line is going to be a perpendicular bisector of those segments. Okay. So, guys, if there was a point where this wasn't true, then certainly it wouldn't actually have symmetry, and that's what we're going to be looking at example 1. Okay, identifying line symmetry. Okay, state whether the figure has line symmetry, right, yes, or no. If so, copy the figure and draw all lines of symmetry and state their number. So, guys, the idea here, we're trying to determine if these do have line symmetry. So, guys, conventions would maybe you're visualizing that, going vertically through. Maybe I didn't do a very good job of drawing it. Let me back up. Maybe this kind of this idea of a center point. Okay. Maybe that we're thinking that maybe that's line symmetry, but guys, clearly you can see the distance to that point to the left and that distance to the point to the right. Well, that's certainly not a bisector. Those aren't the same distances. So that is not going to be a line of symmetry. Bear with me, guys, as I erase that. Something similar is going to happen if we're trying to imagine it horizontal. Sorry about that, guys. Still struggling a little bit. Technology. So if you're trying to think of a horizontal there, so the trouble here, maybe not quite as much as the distance from the line these points would be. Okay, you can imagine the distance here, is going to be very similar to that other distance. Okay, the trouble is, this one I started with, there's no point there. Okay, it's not reflected across that line. So the vertical case, the horizontal case, not working on this figure. All right. Um, last check might be, well, what about the diagonal? That's really poor. Because even me freehanding, this can be somewhat of a challenge. So, point here, guys. If we check the corner and we're really going, you know, as a perpendicular bisector, yeah, those certainly aren't going to be the same distances. So this one has no line symmetry. Okay. 1B. 1B does have line symmetry. It has. Let me give you this. It has one line of symmetry. Could you guys, you know, pause, try to identify that? Okay. So if you did pause and try to think of it, hopefully you found it would just be right through what we traditionally think of the center. Okay. Each point, you know. So that is a perpendicular bisector. Okay, that's going to be true here as well. Okay, those distances are the same. That segment's perpendicular. Okay, so that works any point here. So this yes, it has line symmetry. We'll state the number. Well, there's one. Okay, there's no diagonals or anything we could draw that would provide line symmetry. Okay, 1C, it would have two lines of symmetry, a vertical and horizontal there. Okay, so this would, yes, it would have it, and it would have two lines of symmetry. All right, continue. Whoa. On to the next page here. Rotational symmetry, guys. A figure in the plane has rotational symmetry or radial symmetry if the figure could be mapped onto itself by a rotation between 0 and 360. So, talk about this mapped onto itself. This looks a little different when you're rotating. You can imagine having these shapes on your desk. Any amount of degrees, you rotate it to where it looks like it originally started. So, if you look at this first picture, imagine taking this diamond and rotating it. Well, they're showing you a rotation of 45 degrees. Well, that looks different on your desk than it did when it started. Okay, so if you kept rotating this, and obviously it looks more square here than like a diamond, but if you continue rotating it another 45 degrees to where you've rotated 90 degrees from the start, well, this looks exactly like how it started with. Okay, but of course the points have all rotated 90 degrees. So yes, this thing has rotational symmetry. It's mapping back onto itself. Well, it's doing it once. Okay, it's doing it also, so another 90 degrees. It's going to do it at 180. Okay. Yeah, another 90 degrees. It's going to do it again. So at 270, yep. Okay, well, what if you went all the way to 360? Okay, it mapped onto itself. Okay, so the reason I was kind of highlighting all these cases here, the number of times it maps onto itself is important. That's called the order. Okay, so the order, how many times would this picture map onto itself? Well, 4 times we count. So the order here is 4. All right. To find the magnitude of something, you take, 360. It's always going to be 360, and you're dividing it by the order. So the magnitude of this shape is 360 divided by 4. So the magnitude is 90 degrees. Okay. So trying to do that on these next couple of shapes. Trying to determine whether they have rotational symmetry. So rather than starting, here, I would challenge you, and it's not really a challenge, probably an easier problem if you imagine, starting, this is your 0 degrees. Okay, so when's it going to map onto itself? When it gets to this next vertice. Well, we don't know how many degrees that is, but that's once. next vertice would be twice, next vertice would be 3 times, 4 times, 5 times, each of these being rotations. Okay, well, one last time, it's going to do it again at 360. So between 0 and 360, it mapped onto itself 6 times. So its order, the number of times it mapped onto itself is 4. The magnitude of symmetry is, should abbreviate mag, 360 divided by, oh my guys, I apologize. You guys are probably all thinking I'm crazy as I wrote down 4. How many times did it map onto itself? I'm sure you guys have already got this before me. 6 times, guys. 6 different vertices there. Its order is 6. Okay, I apologize if I tripped you guys up there. Order is 6. Yes, what you were thinking, Mr. Hartman's crazy. It's true. Okay, so 360 divided by 6. The magnitude here is going to be 60 degrees. Okay, order 6, magnitude 60. Okay, B is going to be tough. I mean, if you imagine this being that, all right, so certainly rotating to that next vertice, that distance isn't going to be the same. Here, trying to rotate anywhere, you're not going to be able to find symmetry here. So this is just no rotational symmetry. Okay, C, let you guys think about that one for a minute. I know there's these petal sizes, if we're thinking of them as vertices, like these points of these petals. Well, there's certainly some short petals where we could find those short petals mapping onto themselves. We could also find the bigger petals. They're also going to map onto themselves. Okay, because when we're concerned about this, we only need to worry about it's going to be true that anytime a big one maps onto itself, if we use that same amount of degrees, the smaller one is also going to be back to itself. Okay, same here and same here. So 3 times, guys, there's 3 big petals. That would be 3 as well. But we only need to count 1, okay? So let's do the smaller petals. That's happening. So it is clearly going to be happening, yes. The order would be 3. Guys, magnitude, we're going to be looking at 360 divided by the order. So 360 divided by 3, we're looking at 120 degrees as the order of rotational symmetry. Or sorry, the magnitude. The order is 3. Magnitude is 120. All right. Okay, guys, next we're going to talk about our 3-dimensional options. 3-dimensional figures. Okay, and they're going to have plane symmetry. And they're going to have axis symmetry. So, plane symmetry, guys, you can think of, you guys got 3D figures in your homes. You guys have got boxes, you've got spheres, balls, basketballs, volleyballs, tennis balls. You've got cans, a can of soda, a can of soup. You guys have got 3-dimensional figures in your home that you guys can kind of look at. In fact, if we were in class, I'd probably pass around some things, some 3-dimensional figures, so you guys could hands-on. So it might not hurt to get something 3D, a box or something in your hands where you can kind of imagine this as we talk through it. So plane symmetry, it's really best described here in this picture. So it's going to be mapping onto itself. Let me use a different color. That blue was a poor choice. So if you're thinking of this as kind of think of it as a saw or something, cutting through this box. Okay, if you can cut it into 2 pieces that are exactly the same, that are going to map onto the other piece, okay, then you are, that is having plane symmetry. So this box, it certainly has plane symmetry. It's got it right there if you imagine cutting it vertically, okay. It's also got plane symmetry, if you cut it here, the top and bottom half could be the same, okay. Unlike our 2-dimensional figures, we're not worried about how many lines or how many plane symmetries it has. We're just worried about, does it have plane symmetry? Okay, and then axis symmetry is the 3D version of um, rotational symmetry. Okay, can it map onto itself between 0 and 360? Um, so you're thinking, of think of your tires, spokes, or your parents' car. This the rims on their tires. Um, they typically are symmetric. Okay, where the spokes could easily, you can see how they would map onto themselves. Um, that's a good example of rotational symmetry. Take this hexagon. I appreciate this. It's you can spin it around to where it's going to map back onto itself. Okay, between 0 and 360. I say hexagon. It's a pentagonal prism. All right. Um, it is possible to have both. Okay, it's possible to have both. Um, in fact, let's look at example B. State whether it has plane symmetry, axis symmetry, both, or neither. So, guys, plane symmetry. I'm imagining, well, you could, if you imagine having this in your hands, the plane through the middle there. That cutting this shape through the middle here, you're going to have plane symmetry. Both those pieces they map onto each other. Okay, um, and then you could also consider here, but it doesn't matter. It does have plane. Check. Okay. What about axis symmetry? So axis symmetry, we're thinking. Uh, Probably thinking this axis that view. So how can you think of axis symmetry? You can think of, okay, well, those 2 points that I just made. Imagine holding this shape and putting an index finger on the top point and a thumb on the bottom point there. You could spin this thing around in your hand, that being the axis of rotation. Okay, does it map back onto itself? It does. So this would also have axis symmetry. So this has both. Okay, plane and axis symmetry. You could cut it and it map onto itself. You could rotate it and it map back onto itself. Okay. Now we're talking about this L-shaped prism. Guys, this L-shaped prism, I'll just get to the rotational here, the axis symmetry. This one's not going to map onto itself until it made a whole rotation. So it doesn't have axis symmetry. Okay, does it have plane symmetry? Could you cut this somewhere where it is going to map back onto itself? Okay, well, if we think about cutting it here, okay, obviously this bottom rectangle is going to be much larger than this top, almost looks like a cube. Okay, not identical pieces, so not a plane, not through there at least. What if we thought through here? Okay, well now I think the one on the right part of this, okay, I think that one's a little skinnier, little taller than that left rectangle. So not that plane either. This one does have plane symmetry though. If you imagine taking this L and cutting through the center of it, okay, there you can create plane symmetry that way. So this does have plane symmetry. Okay, guys, your homework 10 to 30, just the evens. I've put that up on Canvas for you all as I have been. A little bit of encouragement, guys. I know it's very different from our regular routine. It's becoming our new normal at this point, and just keep your guys' heads up. I know this can be frustrating for some of you guys. You guys have done a really nice job so far. I've seen a lot of assignments turned in. You guys are present. You're working hard, so I really do appreciate it. Okay, we got to keep that up as we go forward. Okay, we're at least going through April now with this going on. Okay, that being said, we will have an assessment of some sort here on Chapter 9. I haven't decided exactly what that's going to look like yet. but I will get those details out to you because we are 9-6. That's going to be our last lesson here in chapter 9. Um, so we got one more lesson, and then we'll be looking at wrapping up the whole chapter. We will have some sort of assessment, guys. I'll probably be passing out what that's looking like, probably in my video on Thursday, or on Friday rather, off a day here. What that's going to kind of look like, so you guys can kind of prepare for it, and ask questions in that review setting. So, thanks for watching, guys. Keep your heads up. Keep working hard. I do appreciate everybody that's been working hard. So, thank you. Have a wonderful afternoon.